as I say, we've got an awful lot to get through. I've tried to condense into an hour what would normally take one day of our training course. If you could therefore please bear in mind, if you have any questions, if you could please wait to the end, that would be greatly appreciated. We may not have an awful lot of time for questions at the end. We'll see how we get on. If anything comes up as I'm going through this, if you could please put your questions in the chat, then what we'll do is, if we don't have time to go through those questions at the end, if we run out of time, I'll make sure that once we send out the slides with this presentation, that we also address some of those questions as well. Well, address all of those questions as well when we send the information out. I think we've set the recording, so we'll also try and make that available if that all works. If anyone has any issues with this being recorded, then just let some of my colleagues know in the chat. So what I'm also going to do is, so I don't put myself off, I'm going to turn my camera off, because the last thing I also want is for the Wi-Fi to start playing up. Okay, so I think that should have gone on to the next slide now. So, okay, so in terms of what we're going to be covering today, we're going to cover some of the background to the Canadian method. We'll be doing some comparisons against its European equivalent. We'll go through a high-level overview of the Canadian method. Again, there's an awful lot to cover, so we won't be able to go into every unique part of that in minute detail, but we'll do our best. We'll look at how we define the engineering changes that we're making to the railway, and essentially the system safety activities that we would do through the life cycle of these projects. As I say, we might struggle a little bit for time for Q&A. So I do need to caveat some of this. We can't take any credit for the generation of the Canadian method. It wasn't done by us, so we've talked to some of the consultants that were involved in it. So this is our understanding as to some of the background. Again, I think we've had some people from Metrolinx that have signed up to this. So obviously, please feel free to correct me if any of this is not quite right. But so our understanding is that Metrolinx were concerned about how their projects were considering system safety across their portfolio of projects. And as they were starting to look in terms of how this is managed elsewhere across other railways across the world, they looked further into the European Common Safety Method for Risk Evaluation and Assessment regulation, so EU law essentially, and also some CM-REA standards, which I think quite a few of you on the call will also be familiar with. So, for example, CM-REA 50126, 28 and 29. A UK consultant, as I say, not us, was recruited to draft a Canadian variant of the CSM RA that would essentially become part of their internal company process. And I know that this is being rolled out across contracts within Metrolinx and across wider parts of Canada. I know that there's also being a lot more referencing out to the CM-REA standards as well that I mentioned earlier. It was published in October 2020. So it's been published as an express document, so it's not therefore a standard. So it's not been formally reviewed or approved by the CSA Technical Committee. My understanding is that that process is happening, but I know that the CSA group has acknowledged that the development of this document has been made possible by the financial support of Metrolinx in having it produced. And what this document does is it applies to proponents, and we'll come on to some of that in a bit, but making any change to the railway system that is of a technical, operational or organisational in its nature. So just need to bear that in mind for a couple of slides time. So very quickly, in terms of just very looking at system safety as opposed to construction safety, I know a lot of you will know this already. For some of it, it might be completely new. I try to break things down quite basic for my own peace of mind. So hopefully this comes across and makes some sense to people. But essentially the Canadian method addresses the safety of the system once it's in its operational, once this is in operational service and it's being maintained as business as usual. So therefore we're considering the railway once it's in its final configuration, once all the works have been completed. Whereas from a construction health and safety perspective, we're looking at addressing the safety and changing the configuration of that railway, so getting to that final end state. So the Canadian method is looking at the railway in its final configuration. Obviously, as you can appreciate with large and complex projects, sometimes there can be a bit of a grey area. There can be quite a bit of an overlap. So during some significant stage works, it can get a little bit, as I say, interesting as to what is considered construction safety and system safety, because we might be trying to enter into service some elements of a new route when other parts of it are still being under construction next door to it. So obviously that takes some careful consideration. So we've talked about the Canadian method applying to technical changes and looking at the system in its final configuration. And I just wanted to sort of give you some visual representation of some technical changes and failures that may happen that could essentially lead to quite horrific accidents that could occur once the railway is in that final configuration. So some of those technical failures that have led to some accidents within the UK have been failures of switching and crossing equipment, where we've had broken rails. There's been wrong side failures of signalling equipment. So the bottom left picture is at Clapham, where that's happened through commissioning activities that caused a wrong side failure. We've had signals passed at danger, level crossing incidents, and I know that Metrolinx have also released footage recently as well with some of those incidents that have been occurring in their territory. Road vehicle incursions, and I think there was an incident maybe only yesterday in the US where that's led to derailment and unfortunately fatalities with people on the train. I think that was an Amtrak service. And also earthworks and structures failures. And as I say, some of these pictures are from 15, 20 years ago within the UK. Unfortunately, things still don't, bad instances have occurred. So this is around 18 months ago where there was a derailment of a passenger train near Carmont in Scotland. And that train derailed because it struck debris that had been washed out of a drainage trench. So through the investigation, it's apparent that the drainage system and the earthworks weren't actually constructed in accordance with the original design. So actually it wasn't able to safely accommodate the water flows that morning. So it's been heavy rainfall, but nothing out of the ordinary, as it were. It wasn't, say, a once in a 100 year, once in a lifetime type event. It was heavy rainfall, as you'd expect to get in Scotland. And through that investigation, they also realised that actually there'd been no evidence of those final as-built drawings and a health and safety file having been produced to assist with the future maintenance of those assets. So essentially people didn't know that it hadn't been constructed in accordance with the design through the paperwork that had been issued. So again, this is very much another example of that railway in its final configuration, and not just the importance of the safety management through the actual project delivery, but making sure that those as-built records and health and safety files are ultimately handed back to the people that are going to be responsible for maintaining those systems. So it's just extra things that need to be considered. So that's some of the technical elements of things. We also talked about some of the Canadian method applies to operational and organisational changes. Now, obviously, the examples on the screen here. So we've got Deepwater to Horizon, we've got Challenger Shuttle and Boeing Max 737. Obviously, not rail examples, but again, these types of things are obviously very apparent in other safety and mission critical industries, where sometimes commercial and time pressures can lead to us maybe launching new products when they're not quite ready, meeting quotas, commissioning new projects on time. And also it's identified where sometimes there can be a bit of a lack of a safety culture as well. So disconnection between management and engineering teams, where safety concerns have been ignored and where sometimes teams have felt that they've not been able to raise some of those safety concerns. So that's just some examples of, in terms of the broadness, in terms of looking at considering technical, operational and organisational changes and things that need to be thought about. In terms of the Canadian method and the risk management process, so here it is. Don't worry, don't expect you to be able to read that diagram. We'll break this down as we go through the remaining slides and talk you through that. So we've got some zoom ins and some discussion points on each one. But essentially, based on the bullets on the left hand side, I'm not going to read those out now because again, we'll go through those in more detail so that we can save a few seconds. But this is the risk management process within the Canadian method. In terms of differences between the Canadian method and the CSM regulation on which the Canadian method is based, the Canadian method essentially uses a lot of terms the same as the CSM. Some of them have been modified. I'll talk about that in a sec. There's also 24 additional terms that have been included in the Canadian method which aren't in CSM. However, a lot of those terms will be very familiar to not just railway safety practitioners, but railway professionals as a whole. Some of the key terminology differences, so where the CSM talks about proposers of change, the Canadian method talks about proponents. It refers to participants instead of actors, and it also uses the term independent safety assessor instead of an assessment body. And in terms of a proponent or a proposer of change, generally they're organisations such as infrastructure managers. So, for example, Network Rail in the UK are a proposer of the change, and Metrolinx, for example, in Canada would be considered a proponent as well. So in terms of independent assessment, so generally that is the same. As I say, the Canadian method uses the term independent safety assessor, so an ISA. And for those of you familiar with the CM-REA standards, you'll obviously know of the term ISA there in terms of the technical safety assessment work that they conduct in accordance with the CM-REA standards. In terms of the meaning and the scope, as it were, of the ISAs from a Canadian method perspective, it's the same as the ASBO from a CSM perspective. I need to try and change how I phrase this, maybe get myself confused. So the ASBO is looking to see that the CSM process has been applied correctly and that safe integration has been considered. So that is the case from an ISA and the Canadian method perspective. And again, the ISA as an ASBO, ultimately their output will be a safety assessment report that will either be supportive of the work that's been undertaken from a system safety perspective, and if the projects are being safely integrated into operational railway infrastructure, or it may well be unsupportive and it may well list non-compliances, observations and any recommendations that need to be considered. And obviously, if we're getting to the point where we're receiving unsupportive safety assessment reports, then obviously we've not done a good job. Maybe not, we may have done a good job in the safety work that's been done, but maybe we've not brought the ISA or the ASBO on that journey with us. But we'll come on to a little bit of that a bit later. And the Canadian method also includes some essential requirements in Annex C, which is essentially good practice guidance for project engineers and safety managers to follow. And essentially the reason those essential requirements have been included within the Canadian method, where they haven't been included within the European equivalent, is because the European equivalent refers out to a number of technical specifications for interoperability, which form part of another European directive. Again, we can touch upon some of that Annex C essential requirements a bit later on as we get into the presentation. So right at the start of the process, we need to, and we're talking about Canadian method, very similar, as I say, to CSM with this as well, but for the Canadian method, we need to conduct a significance assessment. There's criteria set out within the Canadian method against which the significance assessment is undertaken, and all of the changes that are considered significant, then essentially the risk management process set out in clause 6 needs to be applied. Clause 6 essentially being the flow chart that we had a bit earlier, a few slides ago. But any change not being considered significant, then essentially it's sufficient to justify that decision and make sure that that is recorded. So if the proposed change has an impact on safety, then what the proponent needs to do is decide through having a core and expert group of the significance of the change based on the following criteria. So we need to look at the failure consequence. So what's the credible worst case scenario of a failure for the system under assessment? What's the novelty of that engineering change that we're making? Are we doing things new and novel that haven't been done before? Are we introducing novel systems? What's the complexity of the change like? We talked very briefly earlier on large and complex projects which can sometimes be delivered through multiple stage works. What's the complexity of that? Reversibility, so can we revert the system back to how it was before? A lot of instances we can't. And in terms of additionality, that's looking at making sure that we're not trying to, I can't think of a better phrase at the moment, but I'll go with get away with from having lots of non-significant projects all overlaid on top of each other just to make our lives a bit easier. So we need to take into account all of the changes that have of a safety related nature that have been made on that system through the process. So the little chart that you got there, now that hasn't come from the Canadian method. This is just an example of what's done in the UK on network rail infrastructure projects, where as part of this significance assessment process, various quantitative type charts have been used to try and help determine if a project is significant or non-significant. So is it high risk or low risk from a safety perspective? And network rail are slowly moving away from that now and going into a more flow chart assessment type basis to try and come up with those decisions. And this is one of the things that I'll be interested to see how things pan out over time within Canada as well. But what Network Rail have done is they've taken the European regulation, they've implemented that onto Network Rail infrastructure through a dedicated Network Rail standard. And what they've said in that standard is that you will follow the CSM process. So that flow chart from a few slides ago, you will follow that process, whether or not the change is significant or non-significant. The only difference being that if it's significant, then you will have an ASBO. So in our terminology for the Canadian method, you will have an ISA, but you will have to follow that process no matter what the output of that significance assessment is. So I'll be interested to see if that is also the case as things progress over time in the Canadian market as well. So in terms of defining the engineering change, so if we go back to the top of the flow chart, we've talked a little bit about significance, but in terms of defining that change, so that's done through a document called the system definition. Now the Canadian method, as with CSM, includes a number of criteria that need to be considered and captured within that system definition. They're listed on the left-hand side. So what's the objective of the system? So what's its intended purpose? What's the functions of the system? Not just the system of system level, as it were, but each of the individual subsystems that make it up. What's the boundaries, whether or not physical and functional? And we've got some slides on that in a moment. What environment are we doing the project in? So we might need to consider climatic conditions, the electromagnetic environment, and as I say, yeah, climatic conditions, that's something, for example, on the Carmont project that we would have looked at, that type of information would have been taken into account during those projects. What existing safety measures are already in place? So, for example, on the projects where we might be introducing electrification onto an existing railway, we would have existing measures such as fencing to prevent trespass, and therefore and warning signage that would help limit the potential for people to essentially come into contact with that new electrification system. And what safety requirements are we going to be using as well as part of our work? Now, generally, those safety requirements are identified as we go through the process, and normally in the last iteration and managed in the hazard record. I'll come on to that in a moment. But those safety requirements would then normally be transferred into the system definition at the end of a project. And are there any assumptions that also need to be considered as we go through the process and validated of a safety nature? Now, the proponent would need to make sure that their system definition is made available to each of their suppliers, essentially making sure that everyone's on the same page with what's being delivered. But the suppliers, given their scope of work, they may need to also generate more detailed system definitions. So, for example, some signalling suppliers may need to generate some systems architecture description documents that they use for their purposes, which would just naturally go into more detail into how their systems work and are being applied for those projects that you wouldn't reasonably expect the proponent to include within their system definition documents. So pictures, they help an awful lot. So the phrase "a picture paints 1,000 words," so they can really help with trying to help define the boundaries of the system. So this is just a high-level geographical representation as to where the project's being undertaken. So this is for the electrification project I mentioned a little while ago. We've got some other track maps that can be used. Again, they also help identify what other assets might be in the vicinity of the project works that are being undertaken. So, systems architecture drawings. So sometimes, personal view, I think they can get sometimes maybe into a bit too much detail. But for example, the types of diagrams that are on the screen now, they can help us with especially our interface hazard analysis to make sure that we've covered off all of the interfaces of the system. And also another personal favourite. Now, again, I can't take credit for this one, but I like system context diagrams because they just help provide a bit of context into how all of the systems are going to integrate together. So for example, depending on what level it is that you're conducting your safety assurance activities, for example, if you're doing safety assurance work as the proponent, then you might be taking the high level view at the system level up here. But depending on maybe your scope of supply, and if you're providing specialist equipment, you'll be looking more down into the detail for how your specific systems are working and interacting with other existing parts of the railway. And another reason why I like these diagrams as well is because, again, not only does it help with the interface sort of hazard analysis side of things, as it were, but it also gives a very good, we can use a lot of good guide words here as well to help make sure that we understand what happens if certain functions don't occur or only occur in part or occur late, as an example. Now, the reason why I've captured some of this under the system definition is because it's really important to keep your system definition up to date as you go through the process. So this is the electrification project. The blue lines indicate where it was being delivered in various route sections for ease of delivery. As we went through the process, a few things happened. Certain things got taken out of scope. So I think there was budget issues. So we didn't electrify it to Oxford. We didn't go down through Bath and round to Bristol. So the system definitions needed to be updated to reflect that. But also, it's very important to take into account the final commissioning strategy for the system. So when that was looked into more detail, and we looked at the energisation events that we would use to essentially juice up the system and start dynamic testing and section proving activities, we actually realised that there was a gap between the energization events and where the route section's finished. So if we had based all of our safety argument on a route section basis, there would have been big gaps in our argument for where the actual power would have been turned on. And other instances, there would have been not taken up all of the route section. So if you can, it's always really good to try and take into account the final commissioning activities as well for how you then go and present your safety argument to the independent safety assessors and the safety authorities to help demonstrate that nothing's essentially fallen through the gap and that you've taken into account how things change as you move on. As I say, apologies, I know we're going through quite a pace at this. As I say, lots to cover off. So some of the types of system safety activities that we would look to conduct through the process would be generating our system safety plan. We would conduct some preliminary and system hazard analysis work, hazard management activity, so hazard record. So hazard record is a CSM in Europe and also a Canadian method terminology. So lots of people will be familiar with hazard log if you haven't come across this phrase before. So essentially, if you think hazard log when you hear hazard record, we need to review supporting assurance evidence, complete hazard transfer process, prepare some safety cases, and also a declaration of control of risk, which again might be a new term that I'll come on to in a moment. So the system safety plan defines the safety assurance activities to be conducted that apply to the engineering change that you're making to the railway to essentially ensure that you're safely integrating into the existing network. So these can be put together in lots of different ways and formats. Generally, they need to look at people-based safety assurance, process-based and product-based. So in terms of competencies, roles of people and interactions between different project teams. Process essentially in terms of how you're applying the CSM specifically to this project. There might be certain bits of risk assessment activities that I get identified that need to be planned into the scope of works. And when I talk about the product-based side of things, are we using approved products? Are we using new products? What safety cases are those products coming with? Obviously, if we're introducing a new signalling system, that's going to come with its whole world of safety cases. It's going to have application conditions, safety-related application conditions that each specific application project need to demonstrate compliance with. So there might be some items there that need to be considered from a systems integration perspective in terms of being able to close out those safety-related application conditions that come with the safety critical bits of kit. But actually your engineering change might not just be sort of taking a particular signalling system off the shelf and trying to use it. You might be having to, the scheme itself may well have to lead to significant changes to that interlocking. So recent project we've worked on, it was a new baseline of the interlocking system, and therefore at generic application level, there was lots of safety work going on at the same time that we're also trying to deliver the specific application project. So therefore, we're also constantly having to make sure that we weren't missing anything from a generic application perspective that was happening in parallel. The ideal process would be that you get all of your generic application safety cases at the beginning of your specific application projects, and then it's nice and easy to try and demonstrate compliance to those as you go through. But when things like that are happening in process as well, in parallel as well, then that can get a little bit more complicated to try and manage. Hazard identification. So this is the next step down in the Canadian method process. So the purpose is to identify all of the reasonably foreseeable hazards that would apply to, again, your projects, the engineering change that you're making. Again, for the safety practitioners of you on the call, and there's some of you that I've recognised that I've worked with in the past. As you know, there's lots of different techniques available to do that. And again, depending on the system complexity, will depend on the level of safety assurance and safety analysis that you do. Most common would be hazard identification workshops. but equally, again, depending on the complexity of the system and what level of the projects you're working at, they may well involve fault tree analysis, interface hazard analysis, and failure modes effects criticality analysis. There's a term used, broadly acceptable, and essentially if hazards are considered as broadly acceptable, they don't need to be analysed further, but they would be items such as very low frequency, very high severity events. So as an example, meteorite impact, or high frequency stuff with low severity events, i.e. a paper cut. But obviously, if we start talking about that sort of stuff in our hazard records, then obviously we've probably gone a little bit awry somewhere. So the proponent is normally the systems integrator. So they're normally responsible for bringing all of the pieces of the puzzle together. So looking at design, construction, working with equipment manufacturers and suppliers. They need to consider the operators from, say, like a control center perspective, maintenance teams, but also the passenger and freight operating companies as well that are going to be running the rolling stock on the line. Suppliers will likely need to attend any sort of workshops held by the proponent, but as I say, depending on the changes for their technical systems, they may well have to do their own hazard identification activities and safety analysis. And again, at that level, you would also not only just expect the proponent to have a safety plan that talks through their activities, but the suppliers would generally also need to have their system safety plans, which provides that level of detail in terms of the work that they're doing themselves. So preliminary and system hazard analysis, I won't go into too much detail on this. I'll mainly touch upon the preliminary hazard analysis side of things, because for me, I don't really get too worked up about what your actual project is, but I never really see the need to start with a blank piece of paper. It's very rare that we're doing something unique and novel that has just never been considered before. So very early in the life cycle, in terms of conducting desktop analysis, I think that's a really important activity to get a feel for the types of hazardous events that might arise during your project. So there's lots of information available. There's obviously past projects that people have worked on of a similar nature. There's information in standards, guidance documentation that's been produced, and also some safety authorities also have particular data that they track. For example, in the UK, the RSSB has got wealth of data in terms of hazardous events and various precursors that can be considered for new projects. So for me, I also find that as a very good way of trying to help make sure that you've not missed anything by trying to make use of this good data. And essentially, as we're about to come onto it as well, the output of all of this analysis would generally get written up into a report that can be agreed between various stakeholders. But for the ongoing management of that, the outputs of those PHAs and SHAs would also need to go into the hazard record itself. And we'll come on to a bit more detail in hazard record in a couple of slides. So obviously, it's not just all about fault trees, hazard workshops, and all of that good stuff. Safety, the system safety teams need to get involved in looking at lots of other material that's produced from projects. So designers, and apologies, some of the terminology I'm using, I'm very familiar with from a UK perspective. I appreciate things are going to be slightly different from a Canadian method, Canadian railway perspective. So apologies if maybe some of this terminology isn't quite the same. So designers would normally put together some designers risk assessments. So generally, a lot of that can sometimes talk about risks associated with construction of the particular design that they've come up with. But there may very well be some of that final configuration hazards and risks that need to be considered that we would look to manage within our hazard record. We would need to look at assumptions logs, construction risk logs, supporting design and as-built assurance evidence. So some technical drawings, for example, have hazard triangles marked on them that might need to be considered, that might not have been marked up elsewhere. Normally they should have been, but sometimes that's missed. Are there any outstanding or deferred change requests? So again, for some data intensive interlocking changes, maybe there are some change requests that have come out of laboratory testing that can't be implemented in time. What's the safety impact of that? We need to consider outputs from the quality assurance process. So those of you familiar with the safety case structure from Senelec 50129, which one of the three pillars there of the safety case is the quality management and quality assurance processes. So quality, safety and technical safety. We need to be looking at subsystem product safety cases. We talked about some of the generic application safety case work, which can sometimes happen in parallel if you're a little bit unlucky. And also it may be that we also look to conduct safety audits on our supply chain as well. If maybe the work that they do doesn't normally have to feed into this, we might want to just make sure that things are going in the right direction from the very beginning. In terms of the hazard record, so this is the formal record of all of the system safety hazardous events and their precursors that have been identified through, as I say, hazard workshops, maybe fault trees, some of those other assessments that we talked about on the previous slide, anything of a system safety nature, so that might occur when that system is in its final configuration. The hazard record is the place to put them. So the source of information could be wide ranging and come from lots of different places, but we would make sure that that gets captured in the hazard record. So it needs to contain a description of the hazardous event and the precursors, and there might be several different precursors for a particular hazardous event. We need to talk about the safety requirements that we need to implement that will mitigate those hazardous events. And then also we need to, obviously, throughout the life cycle, start including that assurance evidence as well, which shows that we're going to mitigate those hazards, that we're going to meet those safety requirements as we go through that process. I could probably have spent the whole hour talking about hazard records and still have a lot of stuff left over. They're arguably the most important document within the, not just the Canadian method process, the same as in the European CSM equivalent. That is the key document that's under assessment from ICEs and assessment bodies. And sometimes they can get into a lot of difficulty. And this isn't just a Canadian method thing. It's not just a CSM thing. Hazard logs have always been tricky, right? So they can have a mixture of formatting, which makes navigation difficult as you're trying to read entries across from left to right. You know, can you actually get all the way from left to right and it still makes sense when you get to the end? It's not always the case. Revision history can be quite lacking in detail, poor traceability from source documents. So if we don't understand something, we don't necessarily want to just sort of put our interpretation on things. We want to try and understand the context of that and where it was raised. So can we sort of trace that back to the original source? We might not include evidence as to if there's a specific area or location where that hazard could occur. A lot of stuff might be line of route based, might be applicable across the whole project, but there are instances where things do occur at specific locations that we need to consider. Sometimes these things can get out of control. It's not, you know, it's not uncommon for some of these things to get to well over 1,000 entries. Maybe because there's been no control as to how they've been inputted into the documents. Sometimes there can be lots of variations on a theme, things are reworded differently. Now, in theory, as you get later on in the process, they should be fairly easy to close out. But if you're doing it 10 times over and you're having to spend that time to understand that it is just a variation on a theme, if you don't have the control when it goes in there, then that can lead to problems, because essentially once it's in, you've then got to manage it. I've seen lots of instances where for evidence, we only refer to a document number. It's like, well, that's not very helpful. Where specifically in that document are we showing compliance? Give me a compliance justification statement that refers to a particular clause and a particular document that helps me with that. And again, you know, that can help show how that hazard has been mitigated throughout the entire life cycle of the project, and it's not just been an afterthought when we've been trying to rush to close a hazard record out. So once we've got all of our entries into a hazard record from all of our analysis, now obviously, like all of these documents, they're quite live. They need to be kept up to date as we go through. But the Canadian method uses phrases such as risk acceptance principles, and essentially each of those hazards need to be analysed and controlled through one of three risk acceptance principles. So either application of a code of practice, comparison with a similar system, or an explicit risk estimation. Now, applications of code of practice, so that might be a particular railway standard, it might be a railway group standard, it might be an international standard that's followed. Essentially, again, a lot of what we do on the railway isn't new and novel, so there are generally standards out there to control the majority of the risks that are identified. So most of the time, a lot of the entries in a hazard record can be closed out via a code of practice. Sometimes we might want to say, well, we've done this project exactly the same elsewhere, so we can use that safety argument to close out this particular project. Sometimes I've not seen that done too well, because sometimes it might just be easier to say, well, actually we've met these standards, as opposed to trying to write reams and reams and find lots and lots of information which tries to justify why your project is exactly the same as what's gone on previously. Sometimes it's just easier to refer to a code of practice. And explicit risk estimation, now there's different schools of thought on this one. My one for me is essentially if this is something that we just haven't really come up against before. So sometimes people will say that we need to do an explicit risk assessment where we've not been able to meet a standard. But it's like, well, actually, the code of practice, but actually, we are meeting the code of practice. Sorry, we are trying to meet a code of practice, and where we can't in certain places, then we're doing a risk assessment. So again, it can be one of those sort of grey area bits, but ultimately, we'll get to the same answer. But we need to make sure that that assessment is done, and again, captured in the hazard record for all of our entries. Sometimes, again, what I found is that it can be very easy to blindly just say that we're going to meet a code of practice when you've not really thought about what that code of practice is. But also sometimes we don't go back to principles of trying to understand if that hazard can actually be completely eliminated. So actually, can that existing level crossing be closed? Is there a way to do that as part of our project? So I need to get better at this sometimes as well. Sometimes we can take the easy option, go for a code of practice, but actually, can we take a step back and actually completely eliminate this hazard, and what would that incur to do that? As you guys know, in a lot of instances, we can't, and we need to manage the risk, but it's important, again, that we show that due consideration. Safety requirements. So these are what we will use to have to meet to mitigate the hazards that we've identified. Generally, if a code of practice that we refer to contains that safety requirement, then our safety requirement should be written around making sure that we identify the code of practice and any applicable clauses that we need to meet to safely manage that risk that's been identified. And the safety requirement needs to be essentially based around very similar to how you would do a normal project requirement. So is the safety requirement needed? So is there a consequence if it's not there? Can we actually meet that criteria from the safety requirement? Can we actually verify and validate against it? So is it achievable, verifiable? So as I say, the requirement must be technically feasible, and it must be clear and concise, and etc. I think, and again, the safety requirement would be tied into the hazard record, and there very well may be multiple safety requirements that need to be met to safely manage just maybe one hazardous event that's been identified within the hazard record. So like a one-to-many relationship in terms of hazard to safety requirement. Demonstration of compliance. So we've done the hard work. We've identified the standards that we need to meet. We've turned those into safety requirements. Now we obviously need to make sure that through the life cycle of the project, we're showing how we've met that safety requirement, so demonstrating compliance to those safety requirements. So I've often found that it's helpful to, as you're going through that process, in terms of trying to understand what the anticipated evidence that you will need, what that looks like, as we're going through the process, then we can go and find that evidence as we go through the life cycle. And as I mentioned earlier on the hazard record slide, we need to build a decent compliance justification statement and make sure that we're essentially signposting not only ourselves but any independent safety assessors to show why that evidence demonstrates that we've met those safety requirements. And if it doesn't, what then further do we have to do about it? So the hazard record process helps tell that story as we go. Residual risks and hazard transfer. I think you guys would have noticed that there's a lot of words on these slides. I'm not just trying to read them out. There's a lot of words on here so that in your own time, when you get the slides, you can also give these a bit of a read through as well. Otherwise, we definitely will go over that hour mark, and we're going to be getting quite close to it as it is. So from a residual risk and hazard transfer perspective, so we've identified safety requirements. We've got evidence to show that we've met some of those safety requirements, but ultimately there are still activities that would need to be done to make sure that those risks are managed, even once all of the work has been done and the system's being operated and maintained. So therefore, some of those residual risks may well need to be transferred over to other stakeholders within the process. So as an example, for the electrification projects, electrification into a station which has never had it before, we obviously had to pass on some of the residual elements of that risk to the station's facility operator. For example, they would need to update their safety management system information to show how they were going to brief their third-party contractors that come onto their site to make sure that they're aware of that new electrification risk that would be there to them now that wasn't previously present. Just picking up the pace a little bit. Appreciate a lot of you during your lunch hour, and we'll have meetings to go back to. As we get to the point where we're looking to submit to the independent safety assessors and the safety authorities, generally this will be done through specific application safety cases or safety justification reports. Now, they're not actually phrases contained within the Canadian method, and they're also not contained within the European CSM regulations. What Network Rail have done, for example, is within their standard to implement CSM, they talk about the generation of safety justification reports. So technically, it's not something that would need to be technically assessed against within the Canadian method, but I always find these safety cases, these safety justification reports to be really key documents in explaining the story as to how you think that your system will be safe once it's operated. If people were just to look at a hazard record for that, a hazard log, I think everyone can appreciate that to try and understand that story through a spreadsheet can be very difficult. So to have it clearly mapped out that you've followed your safety plan, that you've conducted all of these types of analysis, that you've managed your hazards and you've closed them out appropriately, I think can only really be done neatly in a document such as this, especially that when you consider that generally documentation is submitted maybe 15 weeks before commissioning. Of course, everything's not going to be finished, but if you can demonstrate how you've controlled that, that you know exactly where you are in the process, what the final pieces of evidence that you require are, and when they're going to arrive, then you can show that level of control to all of your independent safety assessors and safety authorities before you seek their endorsement to commission your project. So declaration of control of risk. So within the Canadian method, it states that the proponent shall produce a written declaration that all identified hazards and associated risks control to an acceptable level. So they don't call it a DOCOR within the Canadian method. So I imagine that they will be called that because exactly the same requirement came up within the CSM, and generally people produced a DOCOR. So that's normally signed by the sponsor, engineering and program and project management leads. And the DOCOR needs to take into account any recommendations or non-compliances that may come out of that ISA safety assessment report. So if they come up with any recommendations, then what you may need to do within the DOCOR or through a letter that maybe supports the issue of that DOCOR is demonstrate how you're going to manage dealing with those recommendations moving forward, and why therefore you still think it's safe to commission the project. So I just wanted to provide a little bit of information about working with independent safety assessors. So sometimes it's something that people get maybe a little bit freaked out about, but generally the ISA wants your project to succeed. It's really important to bring the ISA on the journey with you and engage with them as early as you can within the design phase. They will provide an independent assessment plan which maps out their assessment activities and how they're going to go about doing it. They may well provide assessment records and observation sheets on key documentation so that you can progressively bring those documents up to a level that the ISA is happy with. And ultimately, as we've talked about previously, they'll produce a safety assessment report, which, if all goes well, will be supportive of your project being commissioned. And I think it's really important that if issues are identified as you go through that process, that again, you make the ISA aware of that, because I think if they were to find anything on their own that you haven't told them about, that they've come across by accident, then that might lead them to be a little bit wary about some of the other documentation that's been produced. So engage early and bring them on the journey. I won't go into detail on this. I'm conscious that I've talked about a lot of documents through the process, essentially. So this is mapped against a Network Rail lifecycle process. And the key thing here, there will be equivalents mapped against Senelec standards against people like Metrolinx's processes, for example. Cool, maybe quite similar things, but the key thing here is to pick up on is that generally the work starts early and it keeps going. It's not something you pick up during the end. It's not something you start at the beginning and then just leave it for a while. There's constant work to do to make sure that you're going to safely integrate that new project at the end. So, okay, in terms of looking at stakeholders and what it means to you, so we need everyone within a project to play their part, right? So we need everyone to participate in demonstrating that hazards have been identified, that their causes have been identified, and that, again, that we're bringing all the information together to show that they're being controlled to an acceptable level throughout the project. Everyone needs to contribute to hazard workshops. They need to help in assisting in the generation of safety requirements because, again, discipline engineers like signalling engineers, electrification engineers, they know their technical discipline and specialism better than maybe the safety practitioner. So we need those guys' helps to make sure that we're identifying correct safety requirements. They may well need help in risk assessment work and also provide assurance evidence. From a sponsor and project manager perspective, then it's making sure that all staff within the project are made aware of their responsibilities regarding system safety. We need to make sure that system safety isn't just considered an add-on to a project, that there's sufficient budget to allow for it to happen, that we make sure that we include sufficient activities within the programme, and that final end game of submitting to the ISA and the safety authority is taken into account, so that we're not making those last minute submissions and trying to do things in a rush, because that's what obviously gets those guys aggravated and maybe thinks that you're not controlling the delivery of that project. And also, as I say, they play their part in signing off that DOCOR. So within Europe, that DOCOR is a legal requirement. So that is a legal document that they're signing. From a project engineering team, lots of risk assessment work is done as part of the standard day-to-day activities, but it's important that the outputs of those assessments are captured within the safety assurance work, so captured in the hazard record for ongoing management, because again, it can happen that risk assessments and work is done, gets put on the shelf, and then it's not necessarily a live thing that can easily be traced through. But again, we might need those project engineering and discipline experts to help in generation of risk assessments when we might not be able to comply strictly with a safety requirement or a code of practice. Design teams will need to help demonstrate how safety has been how safety has influenced design. So again, helping make sure that we're identifying all of the right information within our designers' risk assessments, in our technical drawings, making sure that our designs can clearly demonstrate compliance to safety requirements and standards. And again, depending on the contractual setup, it may well be that that design teams need to transfer residual risks over to the proponent that would need to be dealt with once their design has been constructed. So if we know that we're not going to have adequate electrical clearances at a station, for example, then that needs to be managed. So there might be very good reasons for it, but ultimately it won't be the designer, it would need to be the proponent and other people that need to manage that ongoing risk once the system has been built. Construction teams, they have their part to play within the process. So there may be instances, we talked about Carmont, for example, where they couldn't build the system in accordance with the design. So that needs to be raised to people, that needs to be communicated to people, and we need to understand what the residual risks are and what the delta is between the design and that final as-built railway infrastructure. And therefore those construction teams will need to also be involved in helping to develop any further mitigation measures that might need to be identified, that might need to be implemented to make sure that there's no further residual risks that need to be considered. It's important to engage with operational readiness people. So again, with lots of large and complex projects, that's going to involve lots of updates to operational documentation, and some of those might need to account for some of the risks that, again, we've identified during our safety assurance activities. So, for example, some of the operational documents we might need to update would be isolation diagrams or operating instructions. Additional training might need to be given, for example, driver training. Some of that needs to be built into the programme, and we need to make sure that we give them the right information to support those activities and the updates that they'll need to make to their safety management systems. Likely they would need to accept transfer of any residual risks. So we talked about electrification at the station. They'll need to ultimately accept that residual risk, but they obviously wouldn't do that until they've got all of the right information from the project teams to understand how that has been managed to the best of the project team's ability to do so. We're almost there, guys. Apologies, I know we're a few minutes over. And in terms of maintenance readiness, so do we need to consider any transitional arrangements between infrastructure that's been built and before it's handed over for day-to-day maintenance activities? So in some instances, it may well be that as constructions teams that keep those assets maintained until they are eventually commissioned properly and handed over to maintenance teams. Do they require additional training? Is there new types of, for example, there's recent projects where we've worked on where we've had to introduce a new type of level crossing. And no one likes introducing level crossings, but it was a type of level crossing that they weren't familiar with in their particular patch. So they needed additional training. Are the access arrangements okay? Can people get there on time? Are they going to have to use heavy equipment? Can they get it there without manual handling injuries? Have we got the right spares and tooling? Where is that going to be located? Do we need to update maintenance manuals? And this is a sort of system used in the UK, but there's a national hazard directory for areas along the routes. And do we need to add any more hazards into that? So again, from an electrification point of view, we needed to add in more entries to show that maintenance teams would need to consider the fact that this new railway is now electrified. And that feeds into safe system of working and planning for maintenance activities. Now, a little bit about Annex C, which we talked about, which is something that the CSM regulations don't have in Europe because they refer out to a lot of the technical specifications for interoperability. But within the Canadian method, it includes some of this good guidance and technical information within it. So the essential requirements are essentially those from the technical specifications for interoperability, but just don't go into maybe the same level of detail, which is understandable. But from a general requirements perspective, as an example, from a health perspective, we would look to make sure that we would restrict the emissions of any harmful and dangerous fumes, that there's no particular materials that are used that can constitute maybe a health hazard. And also onto the next one, there's also contains requirements specific to each subsystem. So subsystems and how that's broken down, again, is very similar to that of, well, it's the same as that as to how it's been broken down on a European level within the these technical specifications for interoperability. And it does provide some requirements that need to be considered. But again, if we were to look at an example for, say, infrastructure, the Canadian method will say appropriate provisions need to be laid down to take into account particular safety conditions in very long tunnels and viaducts. Whereas the similar sorts of information contained in the TSIs, they just go into a bit more detail, and they might say for tunnel lengths of this size, every 500 meters, you need to have a cross passage. At certain intervals, you might need to have emergency signage and other information such as that. So again, so it's just something to be wary that where this is brought up as a requirement, that the essential requirements within Annex C also need to be considered, and it may well be that, again, similar to a requirements management verification and validation exercise, that providing compliance justification statements against each of those essential requirements would be worthwhile doing, as it's obviously something that the independent safety assessors would therefore have to assess your project teams against. So again, making that visible to them as to how you're addressing it early is certainly going to be very beneficial. Now that, ladies and gentlemen, was a very quick whistle-stop tour of the Canadian method for risk evaluation and assessment for railway systems.